Okay, I'm having pity on you and actually printing out the equations to look a little bit nicer for this video. But I want us to see the distinction between these two equations. Separate those two. Which one would you rather try to find the solution to? Which one would you rather solve? I think we'd be pretty unanimous in saying this one's going to be easier, get it done, move on with my day, fantastic, right? Well, why is this easier? What is it about this equation that makes it easier to solve than this one? Well, there's just less going on, right? I only have one operation here. Here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 operations, and each of those have to be dealt with, right? This is one of the big concerns I have with the way a lot of people approach mathematics. Their eyes focus on the numbers when what they really need to focus on is the operations. It's the operations that guide what's actually happening. So, an even easier equation than this, keep putting stray marks on there, is this. Right? That was one of the first examples we saw of an equation. This is the easiest thing in the world to find the solution to. What's the solution here? What value of x makes this statement true? Well, 2. So we say that's true if x has a value of 2, right? That's basically what this is saying here. If x has a value of 2, then 2 is equal to 2. So the solution is 2. Done. Our strategy most of the time is going to be to use the steps that we're about to look at to turn any equation into an equivalent equation that looks like this. Right? So let's toss that definition on there. Two statements are equivalent, because this goes along with inequalities as well. This word equivalent here means they have the same solution. Let's pull that down so we're not in the way here. So in this context, when we're saying equivalent, I'm not talking about equivalent fractions. I'm talking about equivalent statements, such as equivalent equations. Equivalent just means they have the same solution, right? This statement is equivalent to this statement. Saying x is a little bit more than 13, such that this expression then arrives at 15, is the same as saying x is 2. If I say I'm 13 and my brother's 15, how much older is my brother? Well, that's the same as saying my brother is 2 years older than me. Right? Whatever context we want to create for this statement is equivalent to this statement. Right? So we want to keep getting equivalent statements that are simpler and simpler and simpler with fewer and fewer operations until we've made it all the way to the simplest of all. Right? So how do we do that? How do we go from here to here? How do we go from here to a statement that says x equals some number? Well, the identities are the way to do that. Right? If we look at 5 plus x, I can't take care of that addition without knowing the value of x. If I'm trying to find which value of x is going to work for some broader context, there's nothing I can do here. But if I can get 0 plus x, there is another expression that is equivalent to this, right? I can perform this operation even without knowing the value of x, because anything plus 0 is that same thing. So the key is going from here to here. Now there are two ways to go about doing that. One way is to introduce a new operation. The other way is to use the given operation and use a different number. So, for example, if I have 5 plus x minus 5, I know that I can change the order here as long as the 5 stays negative. I can do 5 minus 5 plus x. 5 minus 5 is 0. Oh, not 0. X. Starting with x, adding 5, and then subtracting 5, I'm right back to x. The problem is this expression doesn't really look like starting with x, adding 5, and then subtracting 5. What I find much easier to follow logically is to not introduce a new operation, but to introduce the additive identity. 5 plus its opposite is 0. And then 0 plus x gives me x. Right? If my operation is addition, I'm going to use addition and the additive inverse, otherwise known as the opposite. Same thing with multiplication. If I'm starting with 5 times x, one option is to go from multiplication to also division, where I'm saying 5 times x divided by 5. Again, this doesn't really look like 5 divided by 5. It looks like x divided by 5, and then something else is going on. I find this more confusing. I think if we go with 5x showing multiplication, and then showing additional multiplication, I can see the associative property lets me associate 5 with 1/5, giving me the multiplicative identity, right? 5/5 is 1 whole. And 1 times x, I can do that multiplication, and I get x. So how do we get from here to something that has no operations? We introduce new things to the equation in order to get either the multiplicative or the additive identity. Now, why are we allowed to do that? Some people call it a principle, some people call it a theorem. Basically, it has to do with a balance. If I have some weight over here, and this is going to stay balanced, right? The teeter-totter is not tipping to one side or the other. This side has to be the same. If I have 13 plus x on one side and 15 on the other side, I'm balancing that. The equal sign is saying this has the same weight as that. They're balanced just the same way. And if you've ever seen a balance where you've got the two pieces, if you put more weight on one side, it's going to tip down. And if you put more weight on the other side, it's going to tip down. So if we put the same weight on both sides, as long as my arms are strong enough, as long as the mechanism for the teeter-totter and the tensile strength of the board, right, as long as everything's strong enough, I can add as much weight as I want on the left side, so long as I add the same amount on the right side, and it will remain balanced. Right? If this is a true statement, an equivalent statement would be something like this. add, that's a plus sign here, add 100 pounds on the left, add 100 pounds on the right, and we get the same statement, right? We get an equivalent statement. 13 plus 100 are like terms, 113. 15 and 100 are like terms, 115. There we go. If this is true, then so is this. Now, this isn't really an improvement over my original statement. In fact, I think this is harder to figure out how much x weighs. If I've got 113 pounds on one side and 115 pounds on the other, well, that difference is actually pretty small, only a 2-pound difference compared to 115 pounds. Depending on how precise my mechanism is here, x might not even have much of an influence. If a fly lands on this side, that's not going to really mess up your teeter-totter if you've got two people sitting on there. Right? If some sumo wrestler comes and sits on one side, but the other side stays the same, that's really going to change the balance. Right? Now, we're assuming for these equations that they're perfectly equal, that our balance is always perfectly attuned. Any slight variation is going to set it off, right? They're exactly equal to each other. But the point remains, adding 100 to both sides is not helpful. The question is, what would be helpful? What would be helpful is getting the identity here. I want x plus 0 so that I can perform that addition. So I'm starting with 13 plus x. And instead of adding 100, I'm going to add negative 13. Right? I'm adding this helium balloon that's pulling up with 13 pounds on the left side. I'm adding this helium balloon that's pulling up with 13 pounds on the right side. And this 13 pounds of pressure pulling up, and this 13 pounds of pressure pushing down cancel each other out, right? 13 plus negative 13 is 0. And 0 plus x, I can perform that operation. 0 plus x simplifies to x. 15 plus negative 13, 15 is forward, 13 is backwards. That's the same as 15 minus 13, which is 2. Right? How did I get from here to here? I introduced a new operation here, adding a negative 13. Since I did it to both sides, it's remaining balanced. And because I chose this new operation wisely, I can combine like terms and then actually do that addition, which is no addition at all. Right? I'm canceling this 13 out by adding its additive identity, by adding its opposite. And that's the key. That's how you solve equations. To solve an equation, now, for this first example, there is nothing to simplify. Right? 13 plus x, I can't perform that operation. If we go back to this example, I'm not going to start adding a negative 8 to both sides because I've got a lot of other stuff I can do first. The first thing we often want to do, not always, but usually the first thing we want to do is simplify each expression. And this independently is key because combining these two like terms has nothing to do with combining these two like terms. Right? As I'm performing these operations, that's completely independent of performing these operations. They're two expressions. So we simplify each expression independently. And then, if that doesn't just lead us straight to x equals 2, Then we introduce the same new operation to both expressions. So we introduced this negative 13 to both expressions. Then what do? Then 13 plus x plus negative 13 simplifies to 0 plus x simplifies to x. It has nothing to do with this 15, right? As soon as this red negative 13 is there, I'm simplifying that left expression. I'm just going back to step 1. To solve an equation, we have 2 steps that we perform over and over again. So let's jump to a new video and see this in action in a few different examples.